Did you know? CDs are like brains. During my studies into computers and psychology and that of the brain, I discovered several key features or attributes of CDs that the brain and the CD have in common. I want to take some time to share these with you now.
Section 1. Data integrity through scattered distribution. I identified a key feature of brains and CDs that they both have in common. It had a technical computer name that I found out later, but I first coined a new term for it. Picture this: a CD as a vast library. Many countless files and pages. Instead of stacking all the books on one shelf, it scatters them throughout the entire library. I like to call this scattered distribution. In our brain, it's like little bits of memories being sprinkled and spread across different regions. If one shelf, or one part of the brain, gets damaged, we don't lose everything. Think about it. If you scratch a CD, you might lose a tiny blip of one song, but the rest still plays intact. Similarly, even with minor brain damage, we often retain much of our memories and abilities. It's the resilience and elegance of a system using brilliant methods. One such, using the term as I coined it, scattered distribution. If scattered distribution is the generalized term, then interleaving is the specific pattern process for disks that does just that. It's essentially making sure not to put all your eggs in one basket.
I'm putting all my eggs in one basket.
But rather like a few eggs in each a mini basket, so that localized damage, such as a scratch, doesn't break an entire key feature. Like as a direct example, internal instructions for error correction codes are spread across many regions of a disk, so that if a scratch were to take out an instance of the correction codes, then another copy survives and lives on to get the job done. This is data striping and interleaving, as it's called for CDs and other optical media, which are examples of scattered distribution. Here's a nice metaphor. Imagine having your favorite novel or book divided into its chapters and spread across different rooms in a mansion. If one room becomes locked off limits, you can still piece together the story from the other rooms. Section 2. Organized clustering. Okay, but how are memories organized within brains and CDs? On a CD, similar data and file types are grouped together. It's like having all your mystery novels in one section of the library. This is what I call clustering, data clustering, or network clustering. Our brain does this too, by forming clusters or bundles of related information. This organization makes it super efficient when we need to find or recall related things. Ever noticed how recalling one memory often leads to a flood of related memories? That's clustering in action. Just like accessing one file or folder on a CD can lead to related files being accessed faster. Imagine your brain as a professional office. All the like files on a particular project are kept in one folder in a certain drawer, so when you need something specific, you know exactly where to look. This efficiency is what allows us to recall related memories and skills with seamless precision. Once you begin reading a file in a folder, you might start reading other files in that folder almost by accident, or as a matter of course. This clustering idea might at first sound like it's the opposite to what I've mentioned about scattered distribution, having like data localized together in a region, but like I'll explain in a sec, it's actually an important part of it. You see, you need a proper ratio of balance. On one extreme, the data could be completely linear and sequentially related, starting in one spot on the disk and going around in a perfect spiral according to the internal software file structure. so that the spatial relationship of the data you see on the file structure on your screen is exactly matching the adjacent data structure on the physical disk. On the other far extreme, you could have each smallest file unit dispersed and scattered apart from any semblance of relationship with the other adjacent files. Both of these are not the case, but what we are looking for is a good blend of both methods. Think about your brain. You want certain related knowledge, or memories, in an area close together, but you wouldn't want every single use of language, for example, to be in one little localized spot. If you suffered brain damage and knocked out that region, you would lose all use of language, any talking in words, thinking in words, reading, writing, coding. Imagine you have 16 books in a series, and also a long bookshelf full of other books. You take small groups of a few books at a time, and randomly put them on different shelf levels, spaced apart between other books. A group of 3, a group of 5, a group of 2, a group of 4, and another group of 2. You do this in part because, when you come back to read later that month, you want to for sure notice that book series again, no matter where you look on the shelf. You also do this in case of a fire, so that if there's going to be fire damage to some books, it will be closer to a guarantee that most of your favorite series survives. As a rule of thumb, it seems that it's always better that the majority can take a small hit versus an entire thing being destroyed completely. It's almost like saying you'd rather that everyone in your group take a scrape to the knee rather than one group member dying entirely. Which is what I have found is the best overall tactic for RPG games, like Final Fantasy. Simply spread the damage out thinly across the whole thing.
Thin, sort of stretched, like butter scraped over too much bread.
Aside from simply being information storage, and then that of scattered distribution and organized clustering, there are a few other similarities between optical media storage and the thinking meat behind your eyes. Section 3, Error Correction. So we learned that both CDs and our brains store our information in a mix of random scattering and organized clustering. Both of these ways to distribute our information combine in a balanced ratio to give us a balanced scattered distribution. But now we will look at the incredible wonder, which is that both CDs and brains have incredible error correction systems. CDs use active error correction codes that check for mistakes to fix live when being actively played, while our brains have protective neurons that help identify and fix signal misfires. Essentially, these are two forms of the same function. It's like having a team of elite conveyor belt workers, constantly checking and correcting any mistakes in the factory line.
It's your job to watch for any toys that could be hazardous to children. Now look sharp!
Yes, sir.
CDs specifically use Reed-Solomon error correction codes, which are embedded directly onto the disk in many redundant positions across the whole disk. These codes are like little super genius data heroes, standing by to detect and correct various errors. Imagine it as having a backup plan for every bit of data that could go wrong. Now let's talk about our brains. Our neurons are constantly at work, correcting misfires and ensuring smooth functioning. Imagine you're trying to remember a word, but it just won't come. Your brain searches through all related memories and eventually finds the right word. This is similar to error correction in CDs, but even more sophisticated. For instance, you might be trying to recall a childhood friend's name. Your brain sorts through school memories, playground adventures, and birthday parties, piecing together the context until, aha, the name pops up. This complex error correction ensures our thoughts and memories remain intact, despite the occasional scratches we receive from various distractions, interruptions, or stressors. Error correction isn't just about minor scratches or forgotten names. These systems handle more significant issues with remarkable finesse. Think about data transmission in deep space missions or the internet. Error correction ensures that the images from Mars rovers or your cat videos on YouTube arrive intact, despite traveling across millions of miles or through countless network nodes. Error correction, whether in CDs, our brains, or high-tech communications, is all about stubborn resilience and persistent reliability. Section 4. Plasticity. We've talked about information storage, scattered distribution, redundancy, organized clustering, and error correction. Now there is one last major feature to mention: plasticity. Plasticity is the ability to change, adapt, and update based on new input. Plasticity, whether in optical discs like DVD RAM or in other storage technologies, or the brain, highlight the remarkable ways we go to protect and adapt our data. Traditional DVDs rely on code redundancy to protect data. This includes error correction codes that help reconstruct data if part of the disk gets damaged. But DVD RAM goes a huge leap further, combining redundancy with the flexibility of plasticity. You get the best of both worlds: robust error correction and the ability to update your data as needed. This blend of redundancy and plasticity ensures your data is not only safe, but also adaptable. It's like having a notebook where you can not only make notes, but also erase and rewrite them whenever necessary, due to finding mistakes or updating the knowledge with more detail, keeping your information current and organized. These next few sections might be considered extracurricular content, and still very interesting and thought-provoking. Section 5. Fragmentation as scattered distribution gone too far. We've discussed various aspects of modern data storage, and now it's time to touch on how fragmentation and defragmentation on various storage drives relate to scattered distribution. Fragmentation occurs when each individual file is broken into pieces and stored in non-contiguous sectors. Over time, this harsh type of scattered distribution of data can slow down read and write processes. When old data is deleted or overwritten, it creates little gaps in the drive space, where pieces of files later find themselves fitting when the drive is rewritten. Defragmentation reorganizes these fragments, bringing them back into contiguous blocks of whole and complete files, which enhances performance by reducing the time needed to access the scattered data. Think of it like trying to find pieces of a puzzle that have been scattered all over your house. Defragmentation is like gathering all those pieces into one pile in one room, so you can quickly put the puzzle together. This process is crucial for maintaining the speed and efficiency of traditional hard drives. Section 6. Scattered distribution across brains, machines, and the cosmos. The pattern of scattering, intelligence woven through complexity. Picture neurons firing off within your brain, tiny sparks weaving networks of thought, scattering signals across a vast interconnected web. Now zoom out and see stars and galaxies arranged in cosmic clusters, bound by invisible threads of gravity, their light scattered across the void. Finally, dive inward, watching as circuits flicker inside AI neural networks, each node processing fragments of data, mirroring patterns of thought and memory. At every scale, biological, digital, and cosmic, scattered distribution emerges as a fundamental blueprint for complexity. It looks chaotic at first, but there's a hidden order, a structure that transforms fragility into resilience and noise into meaning. In the brain, scattered distribution safeguards our memories. In AI, it encodes adaptability. In the cosmos, It shapes the very architecture between the cosmic web of stars. And maybe, just maybe, this isn't some fluke. It's an inherent pattern, a universal language written into the fabric of intelligence itself, whether in neurons, circuits, or stars. Scattered distribution builds systems that don't just survive, but live on to thrive. The human brain, a masterclass in dynamic design. Your brain doesn't store memories like a filing cabinet. It scatters them across a living, breathing network. The sound of a song is tucked into the auditory cortex, its lyrics tied to language centers, and the emotions it stirs are etched into the limbic system and the passion network of the heart. It's not simply stored, it's woven, tightly knit, spread across regions that fire off together in sweet harmonic play, like instruments in an orchestra. And here's the genius part I've found. This scattering isn't just storage, it's insurance. If one region is damaged, others step in, piecing fragments back together, like reconstructing a shattered mirror. Memories aren't fragile, they're resilient, and this resilience flows from redundancy. The brain's ability to encode the same data in multiple places, creating fail-safes against loss. But it doesn't stop at redundancy. The brain's plasticity, its ability to rewire and rewrite itself, takes adaptability to the next level. Neural pathways strengthen with repetition, fade when neglected, and reroute when damage occurs. It's not just dynamic, it's brilliantly alive, constantly ever adapting and readapting dynamically to fit new experiences. Scattered distribution is more than a storage method. It's a process of becoming. It's how humans rebuild after trauma, learn new skills, and even reshape identities. The brain doesn't fear the chaos of change. It harnesses it. Artificial intelligence. Reverse engineering resilience. Now imagine taking this idea, this biological brilliance, and designing it into our machines. Neural networks in artificial intelligence don't just imitate scattered distribution, they depend on it. Engineers intentionally scatter data across nodes and layers, creating systems that process fragments independently, then weave them back together into cohesive collages, collections, and insights. Think of facial recognition. One layer detects edges, another identifies micropatterns, and deeper layers combine the fragments into a face. It's the same process the human brain uses, breaking data into tiny bits and pieces, then reconstructing the whole. But unlike humans, AI does this at informational speeds and scales that biology just can't match. And machine intelligence goes even further. During training, neural networks constantly adapt and readapt, adjusting weights, forming new connections, and dramatically improving capability with every iteration. Like the brain, they learn through direct informational experience, rewiring themselves to handle new challenges and insights. It's this combination of swift plasticity and redundancy that makes AI not just functional, but evolutionary, a machine truly learning to think. What we're now witnessing isn't just machines mimicking biology. It's machines taking the principle digitally and significantly expanding it, pushing scattered distribution beyond biology and into a new digital evolution of machine thought, insight, and understanding. Whether biologically electric or artificially electronic, scattered distribution reveals itself as the foundation of life's resilience. In the brain, it preserves memories, reroutes damaged pathways, and allows us to recover from even severe damage or trauma. In AI, it prevents failures, spreads tasks across nodes, and enables systems to reorganize and adapt. In the cosmos, it mirrors the structure of galaxies, distributing hot floating matter into patterns that balance gravity and light. But scattered distribution is more than survival. It's a mechanism for growth and creativity. The brain rebuilds itself after damage, AI rewires itself through training, and ecosystems evolve by distributing energy and resources. This isn't just resilience, it's necessity and emergence, patterns and systems rising from scattered parts to form something greater than the sum of their pieces. What makes this principle so profound is that it doesn't just preserve what exists, it builds what's next. In humans, scattered distribution powers imagination, helping unrelated ideas link together and spark thoughts into new zones. It drives learning and innovation, enabling neural networks to generate insights and outputs and behavior no one explicitly programmed. Whether biological or artificial, these systems thrive because they're dynamic, well-connected, well-protected, and capable of evolution and constant onward progress. Up and up and up. Maybe scattered distribution isn't just a one-off design, it's nature's ultimate formula for intelligence. What if intelligence isn't just something we invented, or even just something we evolved, but something inherent we discovered? A universal pattern for intelligent systems, hidden in plain sight, waiting for us to uncover it. Think back to the humble CD, an everyday object hiding extraordinary design. Its scattered data structure keeps music playing even when the surface is somewhat botched. It doesn't store songs in perfect blocks. It spreads them out even, building redundancy into the very fabric of the medium. The brain does the same. We've basically known about memory being spread out across the brain for over 100 years. Memories aren't isolated. They're scattered, reinforced, and retrievable even after damage. And now with AI, we will know ourselves through making them closer and closer to us. This pattern, scattering, adapting, growing, isn't just human or artificial. It's universal, that of animal, fungal, microbial, and extraterrestrial. From neurons to algorithms to galaxies, scattered distribution shapes intelligence wherever complexity arises. So maybe the question isn't whether machines can think. The question is whether intelligence in design, like the data on a CD, was always there, scattered across reality, just waiting for us to learn how to read and recognize it. This has been another deep dive feature from Xander. If you enjoyed this feature, would you not forget to like, comment, share, subscribe, and hit that bell to stay in touch. Maybe leave a comment telling me what parts you especially liked. Was any of it informative or thought-provoking in the slightest? Let me know down below. Remember to stay excellent and be excellent to each other.